Okay, so let's get started, right? Okay, welcome everyone. Welcome also to the people online. I'm not sure if one of the organizers, if you can check the chat online in case there are questions. So for people online, if you have any questions, please send on chat and I'll try to address them. Okay. Yeah, no, I'm trying to, sorry. Okay. Okay, so before we start, I would like to take, hands up kind of poll to understand where everyone is. So let's start with the professors. How many professors do we have in the audience? Please raise your hands. Okay. Okay, thank you for coming. How many PhD students we have? Okay. How many master's students we have? Okay, no, very nice. No. How many bachelors do we have? Okay, welcome. So that's good. No high school students? Okay. Okay. So now I would like to know how many electrical engineers? Okay, large majority. How many computer scientists? Okay, we'll need your help. How many non-electrical, non-computer science engineers? Okay, none. Okay. How many have taken more than one course in AI? Okay. How many have taken one course or are taking one course in AI? Okay. Okay. Now, how many have used or are using GitHub? Okay, so everyone, okay, yeah, I don't want to ask the other questions so that you don't feel, so that's good. How many, know Python? Okay, so that's good. Okay, okay, so I think we're going to be fine. So so we are going to, yeah, we'll have a little bit of a discussion before we really start. So the course is AI hardware, but of course, in AI, you cannot do anything just hardware. So, a lot of stuff is actually going to be using tools, using Python, using all kinds of, software, so to speak. So again, the goal is for everyone to get an understanding of the hardware, but you cannot really do that without having software. Now, in terms of the actual, hardware, when you talk hardware, we mean something physical that we can touch. Initially, when we put this course together, and the schedule still has that, but we won't have that. There was an idea that we would use FPGAs. How many people here have used FPGAs or are? Quite a large number. So it would have worked. Unfortunately, it was very hard logistically to bring FPGA, boards from the US. They are kind of large. And so what we are going to do in terms of hardware, so that you know up front, we are going to focus on kind of CPUs and GPUs first. But of course, and that's where the Python and all that is going to come into play. But of course, we won't have access to the actual, so this will all going to be in the cloud. But we are going to try to understand, the difference between using CPUs versus GPUs for AI, tasks. In terms of hardware, we are going to have things to put our hands on, hopefully not too aggressively so that we don't break them. But these are going to be what's called TinyML. So these are going to, and we are going to talk about it in lectures and all that, but we have a number of TinyML platforms, 3 platforms, 2 boards of each. So these are going to be the only, so I don't want you to be disappointed. We are not going to have FPGAs, unfortunately. It was just too much. So we are going to basically have exercises after the morning lectures every day. And we'll start with the ones in the cloud on CPUs and GPUs. And then we'll go to the TinyML ones in the second half of the week. Okay, so those are kind of the introduction. Now I would like, any questions, any comments, anything that you guys, and by the way, I would like this to be a little bit interactive. So we are going to spend, 5 days, almost full day every day. It's going to be boring if me and Professor Ambika are going to, our mouths are going to get very dry. We need a lot of chai. So I would like you to be, to engage with us, okay? So especially for people that are, more experienced in AI, I would like you to ask questions and hopefully I'll know how to answer. I should also mention that for people that are not so, experts in AI yet, hopefully you are going to become a little bit more experts by the end of the week. But I would encourage students to work in teams, in groups of maybe 3 or 4 on the assignments so that you can help each other, you can, again, exchange ideas. I'm not sure, so Professor Ambika, is there any kind of grading? I don't know, that's beyond my pay grade.
As for the GYAN policy, you must have some evaluation.
Okay.
Maybe like based on the assignment they will submit or based on the objective questions at the end of this
right.
course. Maybe we can decide later on.
Yeah, so the 2 of us need to figure out, but I would really encourage people to collaborate. Especially at the beginning of the class, because otherwise, it's going to be tough on everyone. And we don't have that, if it's a semester long, you have time, this is a relatively short time. The other is that, again, Professor Ambika's students are, assumed in the round, they are going to have a dual role. They are going to kind of take this class, but also hopefully help everyone else. So they are there to provide some help. We are giving them advance notice of the assignments and all that. And I hope, again, if you are in the audience, please work on them ahead of the other students so that you can help. Otherwise, it's going to be really hard on me and to deal with everyone else. Okay, so any questions, any comments, anything? And that includes people online. Yeah. Mm-hmm. Mm-hmm. It's not available. Let's take that. It's not trivial because we use a system that's kind of internal to UVA. But I can definitely make the lectures of. Let's do that at the end of this course. I want questions now about the beginning. But yeah, that's a good idea. I'll try to see if definitely.
So ultimately, this course is going to be being recorded, so might be then after it will be available, might be different.
Sure, sure, sure. But I think they are right. There's going to be a little bit more, information in the long one. Yeah. Other questions? Yeah.
Are there any concepts that you want us to brush up before coming tomorrow or something?
Well, for the lecture, not that much. The brushing up is going to be for the assignments, because but again, I'll go over the assignments at the end. There's going to be an assignment for today. But yeah, we'll talk about that later. But yeah, all these questions about GitHub and Python, and then how many actually, yeah, that's another one. How many have used Jupyter notebooks? Okay, so a number. So we are going to use this concept of a Jupyter notebook also, which again, so yeah, we'll talk about them. Don't worry about that. Other questions? Those are good questions, though. They're a little bit too, for things in the future. Okay, so I'm trying to understand the question. Digital versus computer. For AI, those are kind of synonymous in some sense. I mean, yes, there are some digital, well, yeah, so for example, these TinyML things, in some sense, they are not computers, but as you know, nowadays, everything is a computer. A self-driving car is a computer. It just has wheels. So yeah, it's kind of both. And actually, there's going to be some element of analog also. You'll see in some lectures we are going to talk about. We are not going to experiment with that, but yeah. Anything that's, we'll talk about all of them, all of the above. Yeah. Other questions? Okay. And I'm not sure whoever, I want someone to really monitor the chat online, please. Yeah. So if there are any questions, you need to raise your hand and let me know. Oh, okay, yes. Yeah, no, thanks. Sorry. Yes, that's an important part, but it's really orthogonal. I mean, I know that the security people, I collaborate a lot with security people, and they try to convince the world, the designers, that security should be there from the start. And, designers have enough on their plate that they kind of do security after the fact. Yeah, that's a good question and an important topic, and I wish you luck in your research if you're doing that research, but we are not now. I mean, you can ask questions and I'll try to answer, but I'm not going to cover that.
Something on my lecture, I will be covering few of the primitive hardware security.
Okay, cool. Cool. Okay, you see, so we are really complementary. That's great. Yes. Yes. Okay, so let's get going. And this slide again, because I took it from the course that I taught last semester. It's already dated because it refers to the it shows the H100. What?
No, I was asking for a pointer.
It's fine. I can, yeah. So the H100 used to be the state of the art, but of course, NVIDIA just introduced, in January, actually, at CES, they introduced, new, so why AI? Like your dean, school dean said, AI is taking over the world. Definitely, that's true. Now, why AI hardware? Because although, kind of what you see are all these, ChatGPT and kind of the software part, someone still needs to build the computers and the digital systems that run that AI. And, we kind of, that's the role of electrical and computer engineers. But the, you know, the most important thing. I'm not sure why. Okay. So the most important thing is that corner there, which is, you know, AI is not going to take your job, but someone using AI will. So you might as well be the person using AI. So whether you're hardware or software, it definitely pays to learn AI. And, you know, the fact that you are all here, you already know that. Now, when we talk about AI, you know, there are really these two extremes where we talk about AI. So one is in the cloud, and this is the one that, you know, it's the most common to everyone. You know, that's related to all kinds of, you know, again, though any of you that are in data science, you know, that's big data. When we talk about the cloud, the big aspect is training. Yeah, thank you. And then, but on the other hand, you also have this edge. So we have this kind of two extremes. And you see the security is here, so that especially at the edge where, you know, physical contact with the device makes it, you know, trickier in some sense to deal with security. Okay, so again, AI means a lot of things to many people. And again, you know, you have everything from you know, what's called machine learning. There's natural language processing. This is the ChatGPT. There is this speech to text and text to speech, you know, Alexa, all these, you know, Siri, all these voice systems. For the people that were doing AI, you know, maybe a few decades ago, in my time, so to speak, you know, there was a big push on expert systems. A part of AI that's, again, quite important has to do with vision. Robotics is an upcoming one. You may have seen, you know, this is evolving really, really fast also. And very soon it's pretty clear we are going to have humanoid robots that are, you know, closer and closer to looking and behaving like a real human. And then, you know, some of the kind of the classical, you know, planning, scheduling, optimization. These are things that the kind of the signal processing community, you know, is focusing on. The ones that, you know, are, you know, kind of the meat of the modern AI, and that are going to be the focus of this class, you know, are basically the deep learning ones, and, you know, we'll go into details about what it means. So, and this is, you know, for maybe for the computer science people here, that you know, how is machine learning different than kind of computer software programming? And the most important part is that, you know, now with machine learning, computers learn without someone explicitly writing a program telling them what to do. So you can think about, you know, before AI, computers would be very obedient, and, you know, the programmer would basically write a C program, a Python program, you know, whatever program, and would tell the computer, you do this, you do that, and every, small thing that the computer would do would come out of a programmer writing a program and telling the computer very explicitly what to do. There is no, ambiguity. You'd have to do that. Now, with AI, the computers can learn by themselves, which is quite an important difference. And again, this is how the two relate to each other. If you do traditional programming, you have a computer and you feed it, again, your program and some data, and you have some action, some output of the computer. With machine learning, the computer still runs some software, but again, that software has nothing to do with the actual task that the computer has to do. You just feed the computer some data, and you feed basically, and this is during training, you feed the desired output, or the desired behavior, and then the computer learns by itself how to deal with that data so that it gets the right behavior. So it's kind of a complete reversal of the, of the traditional programming paradigm, in which you teach the computer by giving it examples. Okay. So any questions up to here? And again, this can be very boring for people that already have taken AI courses. So we'll, the first, actually a relatively long time, we are going to look at the history of AI. And
Okay, so you can increase the volume.
No, no, it's fine. Okay, okay. Okay. Okay, so let's get going.
I think it's.
Yeah, no, just let that out. Don't push it in. Okay. Yeah, so history is important because that's how we understand how we got where we are. And something that might seem, maybe in retrospect not so much, but the history of AI is as long as the history of computing. Of electronic computing, I should say. There are some arguments that there were, mechanical computers with Babbage and even before that. But really, the electronic computers were started in the middle of the 20th century. And really, unfortunately, it was probably because of World War II that really pushed the need for, speeding up computation actually to know how to send missiles, I guess, and bombs better. But nonetheless, that's when computers were first invented. Turing had some role, von Neumann had some role. But what's interesting that from the beginning, and again, in retrospect, maybe it's not so surprising, the people that were working on computers were already thinking about having intelligent computers. And, the Turing test, which is, something that already the modern AI systems have, are passing the Turing test with no problem, was invented at that time. And again, the Turing test, for those of you that don't know, is basically having a computer that can converse, have a dialogue with a human, and the human cannot tell whether that's a computer or not. That's really the Turing test. But basically, it went, and every few years there was something new that came. So the famous paper by Turing, Computing Machinery and Intelligence, famous conference in 1956, where a bunch of very smart people, Minsky, Shannon, and then basically the first hardware that was specifically for AI, which was the perceptron. So let's get a little bit into details. So again, the first important idea, which is still, the kind of the work for hardware people, you can think of the perceptron, this kind of artificial neuron, in some sense is like the transistor for electronics. Most of the electronics that we build is made out of transistors. Nowadays, even, most of the AI systems still kind of can trace their, origin to this concept of a perceptron. And it was a very simple idea. It does look actually like a digital gate. It has a bunch of inputs. These inputs are connected to, a neuron, but, this is like a gate. And there are some weights and the bias. And basically, you multiply the input by the weight, and you add it to all the other input times weight. And you get a sum here. And then you have what's called an activation function. At the time, the way Rosenblatt, who invented this, did it, it was basically just a threshold. If the sum of all these inputs times weights was larger than that threshold, then the output would be a 1. And if the sum is less than a threshold, then the output would be a 0. And basically that's it. This was, the perceptron, and quite some time ago. Now, again, this is a hardware class, so this is how basically a perceptron machine. So they actually build, you can say it's a computer, but it's really not a computer. It's made just out of those perceptrons, and you can see the size. This is basically like a big rack in a room. Computers used to look like that, by the way, at the time as well. So anything that was a computer looked something like that. And in many ways, that's the reason you may have heard T.J. Watson, who was the the CEO at IBM at the time, who said there's maybe need in the world for maybe 5 computers. So the idea at the time, and it's kind of interesting that nowadays with AI, we are in a similar situation because the idea was that every country would have one computer, really large computer, and that's it. With AI right now, there are some efforts in that direction where every, what is that? No. Where nations now are thinking for security and sovereignty issues to have an AI system that's, the nation's AI system. So it's kind of interesting. But anyhow, that's how computers used to look like, and that's how the first perceptron machine looked like. Thank you. Kind of change, relatively quick in the evolution was to replace this simple thresholding for the activation with a more arbitrary function. That's how neurons have become what they are now, as you may know from, again, if you took classes. So that was kind of the first idea, how to have one neuron. Now, obviously, with one neuron, you cannot do very, difficult things. So the next kind of idea was to have multiple layers, which again, in retrospect, sounds like a trivial thing to think about. But this was a very important concept at the time. At the time, they were really not that deep. There was this concept of a hidden layer. You typically would have maybe 1 or 2 hidden layers. But that was a big, big advancement because it really allowed some kind of progress that was not possible with just one layer of perceptrons. So this is an example that kind of shows graphically the advantage of having hidden layers. If you don't have hidden layers, a perceptron is really just a linear function, and this is not a very good figure, but you can probably see that there are some dark and a little bit lighter dots. And the goal of this exercise is to basically classify to separate the dark from the light dots. And again, with a simple perceptron, you can do a relatively poor job. You have a line and you separate, most of the dark ones are here, most of the light ones are there, but there are many outliers. If you have a relatively small number of hidden layers, you can do much better, but there are still a few outliers. If you have, a very deep neural network, and that's kind of, the justification for going to modern, very deep neural networks, you can see that now you can basically separate the dark ones from the white ones almost perfectly. A big problem at the beginning, and one reason why people didn't go directly to these deep neural networks was training. The first neural networks, like the perceptron and the original ones, were really, there was no training. In some sense, those were like the old paradigm. There was a human that was basically manually adjusting the weights and hoping to get the right behavior. And for some simple problems, that was not that hard. Then that was relatively easy to automate for kind of single layers where there are no hidden layers. But the problem is that once you have hidden layers, no one could figure out how to teach basically these feed-forward layers to how to train them to do the right thing. And the important progress here was this concept of backpropagation. And we'll talk a little bit about that, but just to give you an intuition, and again, this is boring for people that already have taken courses in AI. I apologize for that, but for those that haven't, I feel the need to go over this. The idea is this, that at first you start with kind of random weights, and you apply the inputs. And again, the typical example is what's called classification. So, recognizing cats. So you have an image of a cat that's put on the input, and on the output, you can have cat and non-cat. So let's say it's a very simple binary decision. If it recognizes a cat, the output should be 1. If it doesn't recognize a cat, the output should be 0. And when you start with random weights, clearly at first, the output is going to be random. So sometimes it's going to be 0, sometimes it's going to be 1. And what you do, again, with backpropagation, you basically use that information, and when the output is not the right one, then you call that an error, and basically you need to adjust the weights to get the right output. Now, this adjusting of the weights, and now you bring some concepts that are very common nowadays in AI. The error is also called as the loss function. And again, there is a lot of effort has been over the years on different types of loss functions, but that's not so important. The idea is that you want to see the effect of each of the weights on this error or on this loss function. So, and you want to basically adjust the weight so that you reduce the error. And you do that for each of the weights. And the reason this is called backpropagation is because it's really using this chain rule of differentiation of derivatives. So basically, if I want to have the partial derivative of the loss function or error with respect to one of the weights, I can basically go backwards. That's why it's called backpropagation, and do, the derivative of this error with respect to this weight is going to be the derivative of this error with respect to the previous output, and then times the derivative of the output to that weight. And you can basically go backwards like that, and you get all these derivatives. And the nice thing is that when you do the computation, that's one advantage of backpropagation, is that you can reuse some of these partial derivatives during the computation. You don't have to keep computing them. So this chain rule is kind of, and by the way, what's interesting about backpropagation, again, historic, is that it was invented and reinvented several times. So people have figured this out, and I think, yeah, this is a good time for a parenthesis. For those of you, especially for the PhD students, you know how important it is to write papers, right? For you to be successful. But maybe you don't fully appreciate the importance of making your papers have impact, okay? So, if you just write a paper and it's in your resume and, no one reads it, it's good, it's going to advance in your career, but you are not going to have impact. The important thing for a paper to have impact is for other people to actually read your paper, learn from your paper, use your paper in their work, and, advance. That's how you make impact. And that's a difference with the first people that invented backpropagation. Maybe they didn't realize how impactful it could be, how important it was, so they did it, they wrote a paper, and, no one kind of noticed it until, someone really, made it such that it explained that this really solves a very hard problem that, doesn't really have a solution. And the other important one, I think, is naming things. Having good names for your technique, again, seems trivial, but that's how you have impact. If your, idea has a catchy name that people, it would remind people about it, and and also that's also backpropagation. So again, the people that invented backpropagation before backpropagation became successful did not call it backpropagation. They called it chain rule of partial derivatives. I don't know. So the name, the fact that it was named backpropagation, probably also made it important and impactful. Any comments or questions about this? I think this is an important lesson for the PhD students. Well, for everyone, sorry, I don't want to mean, for the professors also, I'm sure. And, for the master students, you probably write papers as well. So I don't mean, any negative. Okay, so now what happens when you do backpropagation, and again, this is a graphical way to represent a little bit the training. When you adjust the weights, it's not like, the first adjustment is going to be enough to get you to some kind of an optimum. So an optimum, again, I hope everyone kind of understands the informal concept of optimal, but the more formal concept of optimal means that, when you have a trade-off, and in this case, the trade-off is recognizing cats versus not recognizing cats. There are degrees to that, operation of recognizing cats. So the optimum is going to be the one that gives you kind of the best result in terms of this trade-off. And finding that optimum, again, it's optimization is everywhere. But in this particular case, you can think of it like this, where you start with the initial weights, your error was pretty large, and then at every training step, you want to get closer and closer to this optimum. And again, the procedure for this is called stochastic gradient descent. So gradient descent is because you are basically navigating down kind of a gradient, and it's stochastic because, and this is something it's not clear to me philosophically, maybe why it's so important, but in neural networks, randomness is a really important feature, is not a bug. So, and again, that comes maybe a little bit as a surprise because for most of engineering that we do, we want things to be very deterministic, right? If you drive a car, or if you, whatever you do, you want things to be very deterministic. In AI, and maybe we can think about our own biological brains, this stochasticity, this randomness actually helps. It doesn't hurt, and you want it. So this gradient descent seems like a pretty nice idea and relatively easy. The issue is that the landscape, so to speak, of the design space for backpropagation looks something like this. It's not that nice, curve with just one optimum minimum point. This looks more like the landscape around IIT Jammu with all the mountains and valleys and all that. So finding the absolute minimum point is actually very hard because there are many valleys that have, relatively, local minima, thank you. And in between them, there are all these, peaks. And that's another reason. And again, there is a lot of theory here. I'm not going to go into all of it, but there is this concept of a temperature in which, because another analogy of finding the optimum point is annealing, which, think about, and again, this is not an electronic thing, but how a crystal is being formed. So a crystal has all the atoms exactly in the same, position. And if you just take a molten thing and you cool it down abruptly, it's going to be an amorphous, substance. But if you cool it down really, really slowly, then all the atoms are going to arrange in the right place and you are going to get a diamond. So in some sense, that's the idea that you want here. This is your diamond. And, all these points here are, glass, amorphous things. And how you get there is it's an open problem. Actually, no real AI system really gets to be diamond. It's probably in one of these other points. So that was, any questions? So that was kind of the old stuff until the, maybe 80s and 90s. So any questions? Yeah.
Where are we introducing the randomness in the gradient descent algorithm? I didn't understand that.
Yeah, so that's introduced basically in the way you pick So the stochasticity comes when you do your, yeah, so here is where you go. Let me show you here. Yeah, so here is where you do the stochasticity, where you compute the new value of the weight from the old value. So you don't just do it with the deterministic thing, you introduce some form of stochasticity.
Alpha is the
Sorry?
alpha is the parameter where we introduce.
Yeah. Alpha is the right. So alpha, yeah. So you can think of it this way. Alpha, if you have a large alpha, you are going to have bigger jumps. If you have a small alpha, you are going to have a small. And if you are going to have stochasticity, you are going to have them sometimes larger, sometimes smaller, sometimes even going backwards. Because that's the whole point. That's how you can go. If you always, that's why it's called stochastic gradient descent. If you only do descent, once you are down in one of these valleys, you can never come back. So that's why that's where sometimes you actually increase so that you can jump back up. And again, that's also related to the temperature. At the beginning, you start with relatively large temperature, so you do these big jumps. And you know, one analogy you can think, if you have like a ball and you throw it, initially you want that ball to be really bouncy so that it goes up and down and up and down, and then you hope, and then you make the bounces smaller, and you hope that it's already kind of, you know, in one of these valleys. And then, you know, it may still jump up, but, you know, with much less probability. And then you cool it down, you have smaller and smaller jumps until you reach the optimum. Okay, other questions? Yeah. Yeah, so backpropagation is chain rule of derivatives. You've done that in calculus. So when you try to, again, it's, sorry. So basically, you are computing this thing, okay? So this is basically the effect. They cannot hear? Okay. Oh, I messed up. Yes, sorry about that. You are computing the derivative of the loss function with respect to the weight. But, you know, it's not obvious how to do that mathematically. So in order to do that mathematically, so you really just want this to do the gradient descent. But in order to do this, you basically, you can always calculate the local derivative. What happens if I change the input here to the output? And then here, what happens if I change the input here to this output? So again, it's a relatively trivial technique that all of us learn it in calculus, but in order to learn to find out the derivative of this thing to some weight here, and again, this is a very simple example. Usually you have hundreds or thousands of these layers. You need to go backwards. That's why it's called backpropagation. You need to do these local derivatives for every one of them to compute this, so that then you can do this function here. And like I said, the important thing about backpropagation is that all of these local derivatives can be reused for almost everything. So there is a lot of, yeah, so again, you know, if you just do for one, you need to compute them all. But then if you do it, for some other, well, this is a too simple an example, but you have multiple outputs, and then you can basically reuse all these local derivatives for all of them. So yeah. Other questions? Yeah.
What does J stand for? Is it some sort of a matrix, which the weight matrix?
Okay, yes. So you are jumping ahead. It doesn't have to be a matrix. So for example, when Rosenblatt did the perceptron, these were actual hardware gates. So, you had a gate with input. So this was very electrical engineering kind of thing where you had like a circuit. Now in modern, and we'll talk about that, in modern AI systems that run in software on a computer, because you have many of these neurons, trillions of neurons and all that, you don't do these computations one by one. You arrange all the weights together in a matrix, and you arrange all the inputs together, in a vector. And then, yes, indeed, it becomes so. Let me see. Yeah, so this, well, I'm not sure that I have it somewhere. Yeah, I guess you see here you already have the vectors. You could think about just one input and one weight, but again, you can arrange everything in vectors and matrix and do much more efficient parallel computation. But yeah, yes. So these are basically the matrices that we are having everywhere. Other questions? Well, so someone is supposed to tell me what the questions are. Who is monitoring? Yeah, you need.
Like you say, it's very hard for hardware. So there is any other algorithm to replace it?
Differentiation is hard for hardware. Not sure that it's. I mean, again, computers do differentiation. So, yeah. Okay. Maybe let me try to understand the question. And we haven't talked about that yet. But again, AI, as most of you know, has these two kind of phases: the training and the inference. So basically, the training is where this backpropagation and all this discussion of local minima and global minima and all these things come into play. Once the system is trained, then you just use it. You just recognize cats. So first, you want to learn how to recognize cats, and then you recognize cats by just using. It's a feed forward. You apply the image of a cat, and you get the output, whether it's a cat or not. Differentiation is only used in training, not in inference. So because of that, training at the edge, as it's called, is actually a little bit of an open problem. So for those of you in the audience that are looking for interesting research areas, open research areas, in many ways, training AI systems at the edge is an open problem because, maybe that's where the question is about the differentiation. It's kind of hard to do this. You may know that, OpenAI and, for all their GPTs and all that, and everyone now, and that's why there is this discussion of nations having an AI system. You need, millions and billions of dollars and, thousands and thousands of GPUs and CPU systems to do the training of one of these really large AI systems. And it is because, maybe differentiation is relatively hard. But again, from the point of view of, hardware at the edge, you only do inference and there is no differentiation. So yeah, I'm not sure if I answered